Hello and welcome. Thank you all for coming to the session. So Docker's not quite as popular as it used to be, but still pretty popular. So what I'd like to talk today is not going to be very introductory. It's going to be lessons learned and kind of war stories from running Docker in production with JVMs inside now for around a year and a half. So why I care about this and why I'm talking about this is for most of my life I've been a Java developer, or at least in my adult life. And over the last year and a half, I've done something very different. I've been what I'd classify as like a platform engineer. And what I've been doing is building a platform for people to deploy Docker containers, which normally contain JVMs, across a large set of hosts. So I'm working in a very small team now, which manages hundreds and hundreds and hundreds of Docker containers, most of which are have JVMs inside them, and it's using a custom build of Kubernetes. What I want to talk to you about today, though, is a very short introduction for motivations for moving to Docker in production. And you could replace the word Docker with Rocket, with all sorts of container engine. It doesn't really matter what your container engine is. It doesn't really matter what your scheduler is. Because I think you have to have a pretty good reason to want to do this. Because the rest of the presentation is all the problems which I've had since doing that, which might be worth it, might be not. So I'll let you decide based on that. And how I'm going to talk about that and present it is I'm going to show you a bunch of examples. We'll talk a bit about how Docker containers work. So my assumption is that you've used it probably on your laptop, maybe in production. You understand the CLI, but you don't necessarily understand how it works under the covers. You don't understand, you don't understand too much about C groups and namespaces, etc. So we'll go through that. Then I'm going to show you a bunch of tools which I now use on a day-to-day basis for diagnosing problems with JVMs running inside containers. And I'm going to do that using two examples. One's going to be a drop wizard example, one's going to be a Ratpack example. It's not too relevant. I just wanted a thread per request application and a thread per core application. So if you want to do what I'm doing on screen or what I'm showing you on screen, then you can do that. I kind of designed this talk as if it could be a workshop. So there's a Gradle project on GitHub that will build you 3 different Docker images and then a set of Docker Compose files, which can then launch them with different configuration options, so you can experiment and see how JVMs behave differently, depending on whether you're using CPU sets or CPU quotas or CPU periods. If you don't know what Docker Compose is, do not worry. I barely know what Docker Compose is. Just know that it's a YAML file which can then launch a set of pre-configured Docker images as containers with pre-configured parameters. I have no production experience with that, so don't see it as like go and use Docker Compose. As I said, I use Kubernetes. So the example that I'm going to do is this. So we like to build microservices these days. And what that tends to mean is we build a lot of services which make lots of call out to other services, be it HTTP, queuing technology, databases, whatever. So what I wanted was a JVM running inside a Docker container which did something realistic. So each of them do a little bit of computation. So the Ratpack and the Drop Wizard application are exactly the same. If you've not come across Drop Wizard, do not worry. It's virtually the same as Spring Boot. It has an embedded Jetty inside it rather than an embedded Tomcat. But just think of it as any kind of, app server which is going to have a thread per request. What they're going to do then is call out to another HTTP service. And for this, I'm going to use WireMock, which is a really cool HTTP stubbing library. But again, you don't need to know anything about that to understand this talk. What we're going to do then is hit it with some load. I've just used Apache Benchmark to generate the load. And I recreated all of these things on my desktop, which has 6 cores, has 12 hardware threads, and 64 gigabytes of RAM. You might think to yourself, why does that matter? And one of the reasons for moving to Docker is that you abstract yourself away from the underlying machine. You build a Docker image, it goes to production, and you're happy. You don't need to worry about that. But one thing I very quickly learned when I started trying to run Java applications inside Docker containers is you really do need to care about what hardware's under the covers. It does make a big difference. So before we jump into the technical stuff, let's have a quick review of the motivation for doing so. Or certainly this is my motivation. It might not be yours. Hopefully by the end of this section, you'll have a good idea whether your current problem, Docker might be a good fit. So have a think about your deployment model. How do you deploy your JVM to production right now? Who here still runs an app server? Who builds an executable jar with, say, a Jetty or a Tomcat inside? Okay, so we're still more at the app server side. Now, some people don't like them. Some people do not like running them. But they give you one major benefit, or certainly a benefit from my point of view. It abstracts the hardware away so that developers can build their WAR files, their application, and they don't need to worry about what hardware it's running on. That can be deployed. Now, anyone with any experience will probably know that you do kind of care which app server it is, etc., and it will maybe work on your laptop and not work inside the app container. But it does attempt to give you that benefit. Over the last 5 years, I've built a lot more executable jars, completely independent jars that only depend on a JRE, which are then deployed to single-purpose Linux virtual machines or Linux like actual bare metal hardware, and that's the only thing running on the box. And you might have something like systemd managing it to make sure it's running and restarting, etc. And you have to ask yourself the question, if you're doing the latter, so you're doing your executable jar, what benefits are you getting from putting it inside a Docker image? Because you've only really got one dependency. You've got a JRE, and probably potentially you need a port open on that box, and that's about it. So what benefits are we getting there? Well, one of the benefits that I certainly saw was I worked at a company that had hundreds and hundreds and hundreds of applications deployed, and they were single-purpose VMs. And what happens is the traffic to those virtual machines, to those Java applications, it's very spiky. Sometimes it's really busy. I've worked for an online television provider in the UK, so everyone logs on to watch Game of Thrones or Manchester United or something like that. And then there's only a small subset of the population that continue to watch, daytime television and watch BBC News all day. Which means that on the whole, the actual hosts that we're running our Java applications on are typically extremely underutilized. Who here runs in AWS? I've got many, a good chunk. All right. AWS have a really cool tool. It's called Trusted Advisor, and it's quite a funny thing. I don't quite know why they give it to us, but it's AWS telling us how to give AWS less money. Now, I can't think what the business motivation behind that is, but essentially it looks at how you're using AWS, and it tells you whether you're doing potentially stupid things. So this is a real account that I worked on for a couple of years. And what it's saying there is we could save $106,000 per month. Think how many burgers you could get for that. You could hire between 10 and 20 engineers on your team. That is an insane amount of wasted money. And that was because we had a large estate, we had a lot of applications, and they were all running on their own virtual machine, and they're all sized for the peak part of the day. And then what would happen is the rest of the day, nothing would be running, or very little would be running. So on average, they were very underutilized. And you can take a few strategies to try and fix this. You could turn them off. You could have smaller deployables and horizontally scale them and scale up and down, and we definitely did some of that. And we got this number down quite a lot. But in reality, in my opinion, the smallest virtual machine inside AWS, or the smallest thing you can do, say, in your actual physical, say you're using Cloud Stack or something, or maybe you've got real hardware, so virtualization isn't even an option for you. Well, if that's the case, then you kind of need to start running multiple applications on the same host. You need to bin pack them. You need to get as many on as you can, and then you need to move them around dynamically depending on how busy those applications are. Now, who here has tried to run multiple JVMs, not your laptop, in production on the same machine? All right? It can be easy, it can be hard. I used to do a lot of work with Apache Cassandra, and it was extremely common, it's a JVM-based database, to run Apache Spark and Apache Cassandra on the same host, because you're typically doing data processing with Apache Spark with the data inside Apache Cassandra. So these were two very beefy JVMs all trying to run on the same box. So they'd all want all the CPU, they'd all want all the memory, and they'd blow up in a heap. And there's a reason why that is. So the JVM is extremely good at utilizing an entire box. If you actually just run a single JVM on a host and you're not, say, in a really latency-sensitive environment, you might pass 0 flags to it. You might not configure anything. And that's because of JVM ergonomics. So the JVM does not pick its heap size based off some hard-coded value. It bases it from the amount of memory on the machine. How about garbage collection? Say you're running a concurrent garbage collector. How many garbage collection threads do you think there are? Well, that's based off the number of cores on the machine. And the JVM's really good at that. It means that people coming into the JVM ecosystem, I think, get a really good view of the JVM. They run it on the box and it all kinds of works. But when we suddenly shove 10 JVMs on the same machine, then they start to step over each other. And that's kind of the problem which I generally try and fix by using containers. But to effectively utilize them, we need to know what they are and how they work. You know, I think that containers and Linux containers, regardless of whether you're using Docker, Rocket, whatever, it is a leaky abstraction. You need to understand how they work and what underlying hardware is there for you to use them effectively. For that, we need to understand a couple of features inside Linux. So we're going to have a look at namespaces very briefly, because I don't think there's much specific to Java about namespaces. But we're going to spend quite a bit of time looking at how JVMs behave when they're inside control groups. So namespaces are a way of Linux to keep things separate. So let's say that you're running a process and you don't want it to be able to interact with other processes on that machine or see them. Or perhaps you want to divvy up your file system so you can only see a small amount of it. These are the features which Docker uses under the covers. But then you've also got the resource utilization. So how do we divvy up the CPU? How do we divvy up the memory? That's where control groups come in. That's what Docker is using under the covers. And rather than just go through a lecture on what they are, let's have a look at some actual tools that you can use. I use a lot more tools than I used to, or there's a whole new set of tools which I use since I started using Docker and Anger. And you've probably used quite a few of them in your past. I imagine a lot of people here have used PS and Htop and Top. And the great thing about these tools is virtually all of them are namespace aware. If you jump inside a Docker container and run Top, it's only going to see the processes of that container because it's in that process namespace. But virtually no tools, including the JVM, are cgroup aware. So if you jump inside a container and run free, then you get to see all of the memory on the host, which means the JVM does. So start to think about the implications of that. We'll also look at dstat, we'll look at cadvisor. If you've not used cadvisor with Docker, then you will by the end of this talk, hopefully, and a few others. So to give you some context, this is the base image, which all three of the images I'm going to play with over the next, say, half an hour, they all extend from this one. So they're all based on the Fusion base image. Has anyone looked at the Fusion base image? Right, I would go and read about it. Just Google Fusion base image, PID1 problem. It solves a lot of problems which happen when you, say, run Java as the PID1 inside your container. You know, zombie processes, etc. So just go and have a look at that. But the only other thing that this does is it downloads an Oracle Java, it copies in my favorite start JavaScript, which we're going to have a look at, and then sets the entry point to something in the Fusion base image. The respective other applications, the other images, so our Ratpack, our drop wizard, and our YMock, they all just stick in an executable jar and then start Java with a bunch of options. Right, so let's start to see namespaces in action. So who here has jumped inside a container using Docker exec? Feels a bit like you're SSHing into it? This is really dangerous. Never do this in production. What we're actually doing here is we're running the bash process inside the same namespaces and the same control groups as our production application. So what are the implications of that? Well, first, let's see the benefits of process namespaces. So we've jumped in and I've run PS, and I only get to see a small set of processes. If I ran PS on the host operating system, I would see hundreds. There are many hundreds of processes running. Most of these are started by the Fusion base image, so we can ignore nearly all of them. But we can see our Java process sticking there. It's about third from the bottom. It has Java native memory tracking and like diagnostic options. But the problem is, if we then go and do something there, let's say that we grep some logs or we sort some logs. What we're actually doing there is using up the resources of the control group that our production application is running in. So you could jump into here, you could run a command, and you could kill your container because you'd hit the memory limit that you've allocated in, say, or maybe you've allocated it manually or via Kubernetes or Marathon and Mesos, doesn't really matter. But just beware, you are using your production application's resources when you jump in and do this. If we want to see those processes, we can do it on the host operating system. Right? Linux containers, they're not a virtualization technology. They're more of an isolation technology. So we can find the same Java process on the host. It's going to have a different PID, though. we're going to see the host PID. So this same process, which is running as process number 28, on the host operating system, we can see it as 298.95. So try and do as much as you can on the host operating system. So that's the first tip. Which means that we don't need to run things like top and Htop and all those tools that we're used to using inside the container. We can run them on the host operating system. So here, I've started to hit this drop wizard application, this JVM running inside a container with Apache benchmark, and right at the top there, it's using 133% CPU and there's many threads running. Htop shows the different threads. And of course, if you just don't like colorful things like Htop, you can continue to use top if you like, and that doesn't give you the per thread view, and we can see that the Java process 29895 is right at the top there. Now, when we get on to looking how cgroup CPU allocation works, there are a few differences, but this is how I would look at the CPU usage. I'd be doing it from the host. But that can become quite tiresome. You see this little PS at the bottom here? Now imagine if you're on a host with 100 containers all running JVMs inside. How do you find out which processes are for which? And there's quite a few ways of doing that as long as you understand cgroups under the covers. And there are also quite a few good tools which are control group aware. So systemd integrates with control groups extensively. This is like I'm guessing most people running Linux now are using systemd or quite an old distro. And it has a set of tools that work with control groups. It doesn't know anything about Docker. It doesn't know the fact that Docker exists. But because Docker is putting things inside control groups, cgroup ls, so listing the cgroups, it's going to be able to see things inside Docker. So when you do docker ps and you get hold of your container ID, that container ID becomes your control group name. So if I do cgroup ls, I actually get to see my Docker cgroup, and then I get to see the cgroup specifically, because they're hierarchical, for that container, and then all of the processes running under it. So I get to see my Java process running under there. And again, I haven't had to jump inside the container. I don't even care what the PID inside the container is. Now, you might not have that tool installed. So like most things in Linux, everything is in the file system. So there is a cgroup file system that's going to describe everything that Docker has set up for you. So if you go into, certainly on Red Hat distributions, if you go into sysfs cgroup, you can then find your containers. So inside the Docker directory, the Docker, the ID, the container ID has become a directory, and you can go in there. You can see how much memory it's using. You can see how often it has been throttled, it's been CPU throttled. You can see if it's going to be kill and things like that. And this led me to understand an error message that came out of Docker. So a lot of the time when you start things in Docker, what you're really doing is all it's doing is passing options down through to Linux. And sometimes Linux says, no, that is a stupid, stupid option. So look at this one. I tried to start a container, and I said it got a system error. I couldn't write to a file. And that's because the configuration parameter I was passing to Docker was just being passed through, and then I can go and look at actually cgroup documentation to see why that was an invalid value. And even if you're not using Red Hat, say using Ubuntu, which is probably the most popular one for running Docker, go and read their documentation. Take half a day and just go through all of the cgroup and namespace documentation. Because when you come to diagnose problems, diagnosing pauses in your Java applications, having that knowledge is going to be invaluable. So let's have a look at how memory behaves for our Java applications inside containers. So if you're not setting memory limits when you're using Docker in production, there's not much point in using it. All right? If you're just kicking off 12 Docker containers running on the same host and they've got unlimited resources, why aren't you just running them as processes? There's no point. So what you typically want to do is be fair. You want to give this application needs 500 megabytes, this needs a couple of gigabytes, this needs 100 megabytes. And normally you've got something doing that scheduling at a higher level, like Marathon or Kubernetes. But let's say you're doing it yourself. Then you can pass in -- memory 128 megabytes. If we Docker exec into that container, now I told you not to do that, but I'm not following my own advice, and run something like free, then we get to see the whole 64 gigabytes of memory, even though this container supposedly only has 128. And that's because it's just proc/proc, all the information in there isn't virtualized. It's just getting the information from the host, and that's the information the JVM thing. So here's going to be a quiz. Part of my start JavaScript sets the min and the max heap to 256 megabytes. So it's going to pre-allocate all of its heap. It's going to be nice and eager there. We're going to give the Docker container 128 megabytes of RAM. What's going to happen when I start this container? Shout out. Someone have a guess. Anyone? Crash is pretty accurate. Who thinks it's going to be a happy JVM tootling along in its container? No. All right? So the whole point of control groups, the whole point of Docker is to be able to allocate certain resources to certain sets of processes. And if you suddenly try and use 256 megabytes of RAM and you only said 128, it's going to kill it. So one tool that you should just get used to using if you're going to go down the Docker route is dmesg. So dmesg, or if you're using systemd, you can see this in journal control as well. It'll actually tell you when it does that. And if you read all of this, the red doesn't show up very well. Sorry about that. But it's essentially saying, I killed your JVM, it's using too much memory. And it'll give you a breakdown of how many pages each of these processes are using in memory, which is also useful. So you can diagnose why. So a common problem I often have is that a certain process will only use, say, 100 megabytes, but it will spawn child processes. And then they'll use memory. And child processes are also allocated in the same C group. So then inside the dmesg message, you'll see what's been killed. What about this? So remember we had 256 megabytes of pre-allocated heap, min equals max heap. And now we're going to give the Docker container 300 megabytes. Who thinks this container will survive? Not survive. Doesn't care. One person doesn't care about our poor drop wizard application. Well, this will depend on the configuration of your operating system, but this survived on mine. It wouldn't survive on some of the servers I work on. There's a little caveat, though. It's very slow. Orders of magnitude slower. So what's going on? What's our poor little JVM up to? This is something which is more applicable to JVMs than it is to other types of applications that run inside containers. So I went for a cup of tea, and 5 minutes later, it was still running and still behaving very slowly. We can see there from the Docker PS output, they've been running for 5 minutes. Another tool I like to use when trying to work out why my application's running slow inside of a container is cgroup-top. So this is a top, which is not going to give you a per process breakdown of CPU usage. It's going to give you a pure control group. So if you were to start 6 JVMs inside your container for some bizarre reason, then it would aggregate the CPU percentages for you. Our little container there, which I can tell which one it is, which C group it is, based on the Docker ID, has 12 tasks. It's running at 356% CPU, and it's using 298.9 megabytes of memory, which is it's what we asked it to use, right? We said don't use more than 300. So it's almost like our JVM is behaving. dstat is one of my favorite tools in the world. If you've not used dstat, just dive in there. Forget about all other Linux tools, or certainly ones which you can do with dstat. So rather than looking at iostat and vmstat and all the stats separately, dstat can do it all, and it's really colorful. So the stuff I would look at if a JVM, say, was not behaving well, is I might just see what the host operating system is up to. So we get load average on the very far side there. So I started this is refreshing every 10 seconds, just before I started the container and just before I started the load on that container. And if you look, the 1 minute load average is below 1. So this is a completely empty, quiet box. We don't need to worry about it. By the time we get to our application acting very slowly, the load average is up to 6, just at the bottom there. We've got all sorts of useful information here as well that you can just have a scan over. The next column is the run queue. So how many threads are actually trying to run on the CPU. Then we've got memory. So what I'm looking at here is there's a lot of free memory. There's 45 gigabytes of free memory, so we do not need to worry about memory saturation on this box. We've got system, we've got context switches. So this is the drop wizard application. So we can see here under system, you've got CSW, which stands for context switches. This is how often threads have been taken off and onto the CPU. And we can see because drop wizard is a thread per request application, we're getting a lot of context switches, but that probably isn't a problem. That's pretty normal. Our actual CPU usage is quite low. We're only using 20% of the CPU as user time and around 13% as system. But the scary thing, something you never ever want to see in dstat when running it in production, is this column, which is paging. So this process is actually swapping, even though we have 45 gigabytes of free RAM. And if we'd look closely at our cgroup top, we'd have actually seen that. This application does not do any disk work. So cgroup top gives you CPU, memory, and I/O. And the I/O actually shows here as it's doing quite a lot. So because we've only allocated 300 megabytes of memory, and then our JVM has tried to use more, this process is actually swapping. And we can go into our other favorite tools, and we can have a look at Htop, and we can see, look, it's using 174 megabytes of swap, even though there are tens of gigabytes of free memory. So this is the slow dying poor JVM. One of the reasons this is more likely to happen is if you do a full GC, for instance, suddenly the garbage collection threads are going to access most of your heap. So a lot of the time you can get away with paging if you don't actually access all the memory that your other processors tried to use. But in JVMs, it pretty much always tries to access all the memory. So we can disable swapping, and to be honest, we do this mainly at the host level on most of our things. But what we do is we pass in memory-swap, and this is memory and swap. So if we set it to the same as memory, then we don't allow the containers to use any swap whatsoever. Oh, I was going to do another quiz. What do you think happens now? It's back to dead. So we're back to looking in dmesg. So as soon as we disable swap, we'll allocate the heap up front. The JVM will use things for thread stacks and native memory, and it will get killed right away. Right, so we need to have a look at memory utilization. And we need to look beyond the heap when we're doing this stuff. Now, if your JVM is the only thing running on a Linux box, I could imagine never looking at this stuff. Unless I had some kind of memory leak or I had something funny with direct byte buffers and caching and things, normally you wouldn't look at this too often. But when you start to run them in JVMs inside containers, I find you just have to do this for every single application. So we need to look at the amount of memory we're using on the heap. We need to look at threads. We need to worry about Metaspace because by default that's unlimited. We have to look at the compiled code inside the JVM. So when your JVM takes your bytecode and compiles it, that uses up memory that's stored. You've got things like GC uses memory. And then you've got any native memory. You could have a library which is using unsafe. You could be using direct byte buffers. And one of the tools that I always have on now inside my JVMs that are running inside Docker containers is the native memory tracking one, but only to summary, so not to full, because that's too much of a cost. So jcommand is a useful tool. If you're not using it on a day-to-day basis, it comes with your JVM now, and everything is slowly moving into it, and other tools have been deprecated, so I would definitely suggest having a play with it. Now, I've broken my rule again now by Docker execing into the container to see what's going on, to see what's using this memory. Now, the reason I have to do this is I don't have jcommand installed on my boxes. I don't actually have a JVM. The only thing running on the host is Docker itself. And if you just run jcommand without any options, it lists out the JVMs for you. So you can find your JVM, then you can run jcommand with the PID and then help. And it nicely gives you some help. And the one we actually want to do is do vm.native memory tracking, native tracking. Depending on which version of Java, whether it's an Oracle versus an OpenJDK, and which version, you'll get a different set of options. But as far as I'm aware, VM native memory is on all of them. Now, what this will actually do is give us a breakdown of all of the different memory regions inside the JVM, which is really useful. So because this was the drop wizard application, and I hit it with quite a lot of load using Apache Benchmark, it spawned a lot of threads. And actually, I only used 12 concurrent requests for Apache Benchmark, but somehow our JVM had created 102 threads, which is quite a lot to service such a small amount of load. And of course, the stack size on a 64-bit JVM is a default a megabyte. So that's actually requiring quite a lot of memory just to keep all of those threads about. Other things we've got on there, we can see the compiler, that's not using much. Internal. So internal is internal to the JVM, but if you start allocating direct byte buffers, certainly the version of the JVM which I'm using at the moment, it would show up there. So you need to worry about your libraries doing that. The Ratpack application, for instance, does a lot more of that. Well, the drop wizard one does virtually none, but the Ratpack one, that number would be a lot bigger. And then we can use jcommand again to get a thread dump and actually have a look inside our JVM to see what all of the threads are, and then we can hopefully try and reduce it. Now, I know you can signal a JVM to get a thread dump, but I find this to be useful because it comes to the standard out of my console. Whereas if you signal a JVM, it goes to the standard out of the JVM, and then you have to go hunting to where on earth that might be. And if it's big enough, which it probably just is on this screen, most of the threads are drop wizard, so Jetty, request threads. How many do we think? So all of the drop wizard request threads have DW in them, which is very nice. You know, it means I can quickly just grep and see that there are 65. So even though we're only handling 12 concurrent requests, we still had 60-odd threads lying around, being used by the JVM for that. Now, Jetty also has quite a few other thread pools. So selectors, what they are is those are the threads which are interacting with NIO, taking the data off the socket and then giving it to your request thread inside Jetty. Something very similar inside Tomcat and whatever kind of like web framework or web library you're using. Now, by default, we appear to have 24. Now, 24 is quite a suspicious number because we were running on a box with 12 virtual cores. So, because what Jetty has done is it's selected the number of selectors based off the number of cores, which is a really good default if you're the only thing running on that host. If you have 100 JVMs running on that host, it's a terrible default. You'll have hundreds of threads that are just selecting. The same for accepting. So these are things which accept new connections. This is, again, based off the number of cores, and we've got 12 of them. Now, you might think that the worst thing that could happen when I'm running my Jetty or my Tomcat inside a container would be that I've got wasted resources. I've got too many threads. Well, that isn't true. Jetty is kind of clever. What it does is it looks at the numbers you've selected and then tells you whether you're being stupid or not. So on some of our applications, we might say we only need to handle 5 concurrent requests, so we would limit our web server to only create 5 threads for handling requests. You know, why would we want to create more? But if we aren't aware that our JVM inside a container is going to base things off all of the cores on the host, then we can get into some pretty sticky situations. So this was an interesting one. So I've recreated this, so this isn't the actual stack trace from production, but what this essentially is I changed the AWS instance sizes under the covers. I decided to use fewer, bigger machines, more cores, more memory, because I was managing too many computers. And we'd hard-coded the number, or we'd fixed, it was configurable how many request threads we were going to have, so that was 5, but we hadn't overridden the number of acceptors and selectors. So the same Docker image that had been running fine for many, many weeks suddenly would not start anywhere. And that's because Jetty was like, why on earth would you have 5 request threads when you've got 12 acceptors and 24 acceptors? So you actually do need to worry about this under the covers. And of course, now everything is configurable. So remember when I talked in the motivation about JVM ergonomics? And JVM ergonomics were about the JVM making decisions that suited the machine it was running on. Well, we need to do that for all of our libraries as well. So Jetty is just one example. If you look inside your database drivers or any kind of like parallel processing, then it's going to have thread pools, and it's probably going to base those off the number of cores. And even if we set all of those, it doesn't stop us from creating many threads. And one of the differences I found when running JVMs inside containers is I suddenly got very tight. And by tight, I mean I didn't want to spend any money. And that's because I was like, oh, I can fit all these JVMs on that server. Let's try and make the JVMs as small as possible. Let's try and use as few threads as possible. Let's try and use as little memory as possible. But most frameworks and web frameworks, etc., inside Java are thread per request. So we end up with 1,000 threads if we need 1,000 concurrent requests. So there is a solution, though. It's to use Node.js. I mean, we should stop using the JVM. I mean, we're in 2016. No, I'm joking. So there are lots of frameworks inside Java that do not tie a user request to a particular thread. You know, using operating system threads as our almost like abstraction around concurrency is very expensive, you know, because they use up memory, they use up operating system resources. So for certain select applications, we moved away from things like Jetty and Tomcat, and we decided to use Ratpack. That's just one example where you have a number of threads based on the number of cores. Most of those systems are built on top of a Netty if they're network-based. But then you've also got systems like Akka. Not at my current place, but at my last company, we used a lot of Akka. And it's not as bad for those type of frameworks, because they're not going to create 1,000 threads inside your container that's only been given 128 megabytes of memory. They're probably only going to create based off the number of cores. And Ratpack defaulted to the CPU's time too. So does Akka, and so do a lot of other things. So we still need to set it, but it's not quite as catastrophic if we don't. But we don't need to stop with our web framework. I mentioned ergonomics before. So GC threads, for instance. Parallel GC is a good thing. It stops us from having to do full GCs. but it means it's got lots of threads running in the background with our application trying to clean things up. But if we've got 100 JVMs running inside the same host and they've all got GC threads based off the number of cores, then we end up with these hundreds and hundreds of extra threads which bring our systems to a halt. Same for compiler threads. So that's not as bad because that isn't linear. It's a very slow progression with the number of cores for our compiler threads. And then we've got things like parallel streams or anything which is using the default fork join pool. That, again, is defaulted to the number of cores on the machine, and you need to override it if you're going to run your JVM inside a container. What I end up basically having to do is recreate all of JVM ergonomics and make all my configuration dynamic based on the allocation to that container. So much stuff about threads, it's time to actually look at how we allocate CPU for our containers. Who here likes GC pauses? No? I love GC pauses. GC pauses are great because the JVM tells me when they're happening, and I know exactly what they are. You know, you can print time to save point, you can print total time stopped, you can do GC pauses. This is great. It's quite visible what's going on. What I really don't like are pauses in my application for which there is no data about why that pause has happened. And this happens a lot more when you run JVMs inside Docker. So let's talk about that now. So using cgroup-top, and if we run, say, our drop wizard application and we hammer it with some load, it'll use loads of cores. It's on 700% CPU there. That's absolutely fine. Which, again, if that was the only thing running on the host, fantastic. But that's not the point. We're trying to run lots of things on the same host and get some fairness, share out the CPU resources fairly. We can see that inside top as well. Now, this is where I'm going to use some Docker Compose files that are checked into that GitHub repository. And I'm going to go through the 3 different ways in which you can give CPU to a Docker container and theorize about how the JVM might behave differently in those scenarios. So the brute force approach is to use something called CPU sets. What you're actually doing here is saying this container can only run on CPU 1, 2, and 3. So in this example here, I've said that my YMock application, the one which the other 2 were calling out to, it can use 4 cores. It can use core 8, 9, 10, and 11. Whereas my Ratpack and my drop wizard application, they can only use 1 core each. You know, one of them gets core 1 and one of them gets core 2. This works, and your application will behave very much like it would on a normal host. It'll get to go on that CPU. If there's free time on that CPU, your application will proceed. But of course, if I ran this exact same Docker Compose file on my laptop rather than my desktop, I don't have 12 cores, so it wouldn't start. It would say that CPU doesn't exist, so it's kind of brittle. Another disadvantage to it is if we're trying to increase utilization, then this doesn't help unless we were to put 2 containers on the same core, which kind of then just makes it complicated to reason about. But if we were to try and use CPU sets, and then we were to hammer our drop wizard application with some load, even though it would love to use a lot more CPU, it is completely pinned at 100%. It can't go above that. However, none of the container engines these days really support CPU sets. I know Kubernetes doesn't. Marathon, when I looked at it, did not, but might do now. So we need to look at the other 2. So the next is CPU shares. So rather than saying you can run on CPU 1, you can run on CPU, what CPU shares are is saying, given if everyone wants CPU, give quarter of the CPU bandwidth to this process, quarter to this, and a half to that. So what that looks like, whether you're using control groups directly or whether you're using Docker, is setting the CPU shares to some number. Now, the default for some number is 1024. And then you can make other containers relative to that. So what I've done here is I've set the YMock application to get 4 times the amount of CPU as either the Ratpack or the drop wizard application. Now, the big difference between that and, say, using CPU sets is if the Ratpack application is not running and the YMock application doesn't really need all of that CPU usage, then you can burst above. You can use as much CPU as you like if the other containers aren't using it. So looking at cgroup-top with this configuration, my drop wizard application under heavy load is back to using, many hundred of % CPU. A disadvantage to this, though, is who here does capacity planning? Is capacity planning easy? Capacity planning hard? Now imagine if you're doing capacity planning with CPU shares. So you deploy your containers to whatever hosts you're doing, and they're all done with CPU shares. You hit them with some load. How much CPU they get is going to depend on what else is on the machine and whether that other thing on the machine is busy. So it can be quite hard to reason about like how much resources you need for each of your processes. So here's a couple of examples about when things can go wrong. So imagine we have 3 containers running on the same host. Imagine one of them to be a Jenkins slave, one could be a production application. And imagine it ended up having 2 cores. It was quite a small box. You cheaped out on Amazon, you went for the T2 small. If we've got 3 containers and we're running with 1024, 512, 512, then the yellow container will probably get a whole CPU, whereas the green containers would probably only get half a CPU. So what if we hit all of these applications with a lot of load, what do you think happens to the green applications? Well, they get starved of CPU. Your application will pause. But it'll be quite a steady pause. You know, green container will get some, and then the other green container will get some, and it will flip-flop between. Or we could depend upon a 4-core box, and everything will be fine. You know, the one with 1024 should hopefully get access to at least 2 cores, and then the 512 ones would get access to a single core. But sometimes that's not good enough. Sometimes you want to guarantee a minimum amount of CPU time. So the next thing that comes in is something called CPU quota. So this is another number, but this number means a bit more. So the accounting period for control groups is every 100,000 microseconds, so 10 times a second. And what you basically ask for CPU quota is how much CPU time am I allowed per accounting period. So I would say I want 100,000 microseconds of CPU per 100,000 microseconds, which could being the important word, kind of equate to having 1 CPU. Whereas if we looked at our wiremock application there, it's asked for 400,000 microseconds per 100,000 microseconds per accounting period. Now, unless you invent some magical computer, the only way to achieve that, to get more time than the accounting period, is to run on multiple CPUs. However, you're not limited to a particular CPU here. So imagine a GC keeps going on in the background with the Java application. What it can actually do is use all the cores on the machine, and it can wipe out its CPU quota in a fraction of the accounting period. So you'd get, say, 10% the way through the accounting period, and your GC threads, or perhaps just your drop wizard, you know, your actual application threads, will have used up the entirety of your CPU quota. What do you think then happens to your application for the other, 90,000 microseconds? It just stops. Nothing happens to it whatsoever. Right? So you'll be running happily with your user requests coming in, and then you'll just have a blip. There's no nice logs to tell you that's going to happen. It's not going to be something like printed out like a GC was. The JVM has no idea that this has happened to it. So if you generally run this, and then you have lots and lots of threads inside your application, you'll use up your quota very quickly. So I don't use this a huge amount. Also, you'll be able to see this by the CPU percentage that your process uses, that your JVM uses. If you remember back to CPU sets, it was pinned at 100. Right? So it could not use more. It was only allowed on that particular core. Whereas when we come to CPU quota, if there are cores available, it can use up its quota as quick as it's like. So in this example, we're at over 100% CPU for the drop wizard application, even though we'd only kind of given it 1 core by some definition of 1 core. All of this data about CPU shares, CPU sets, quota, and actually there's a really cool metric if you go and look in that sysfs cgroup file system, which actually isn't in cAdvisor, called CPU throttle time. So if you're doing your capacity planning and you're using Docker and whatever's scheduling it under the covers is using CPU quota, and you're curious about, what's going on under the covers, why is my application pausing, why does some of my requests take much longer than others, then you have to go and look at the cgroup file system. But for every other metric, then cAdvisor can get it. And this is actually a GUI tool. It's a tool provided by Google. You can actually run it inside a container on that host. You just have to mount that file system into the container, and it will allow you to graph it. And for me, this is really useful. I don't need to go and look at my settings, etc. This will tell you how many CPU shares it's got, the cores it's allowed to run on, its memory limits, and it actually exposes all the data over HTTP. So if you've got like an external metrics database where you're aggregating like application metrics, We use Prometheus to get all the data from cAdvisor for all of our Docker containers and then take it off and then aggregate it. So that's it for information. If you've fallen asleep and you weren't interested in any of it, but you're still thinking about using Docker in production, I'll just remind you of a couple of little takeaways. So if you're going to run JVMs inside there, you need to size your container based on threads. You need to have an appropriate number of threads. You need to reinvent all of JVM ergonomics. You need to be constantly evaluating which libraries you're bringing in, which thread pools they have, and you need to be setting those based off the CPU and memory that you're actually allowing your container to use. And for memory, it really is about testing. Like, I can't give you an answer for this JVM is going to use this much memory. It really depends on the application. It depends how much native memory it's using. It depends about your live object set. The kind of things you can do and will do for a JVM running on a single host, it's just so much more important on a container where you're trying to cram it down into the smallest possible. So on that note, thanks very much for listening, and I'll stick around for any questions. Thanks. Questions? Oh, has anyone got any questions? Yeah. Yeah, so the question was, what are we using for PID1? It's really important what you use for PID1 inside a container. It's going to reap zombie processes, etc. It's something that's built in to the Fusion base image. They spent a long time building a really small init system that runs specifically inside Docker containers. Any more questions? No? Thanks very much, Tim.